Okay, so I just want to remind everybody that your exam is next Wednesday, a week from tomorrow. It's in Follinger at night. And if you want to sign up for the conflict, anybody who wants to can. You don't need a particular reason. Just you have to do it by Friday at 11:59 on Lawn Kappa. So just decide if you want to do that and sign up if you want. The exams are the same level of difficulty, so don't worry about that. It's basically the same exam. All right, so now I think it's a good idea to start studying now. And so if you go to our exam schedule page, just on the course website, Google Stat 200, and you'll see all the study materials and start with the study guide. It's really long, it's very extensive. And after you finish that, you can, next week, you can do the practice exam, which is last semester's exam, is a real exam, and then you should be really set. I'll send you more instructions on how to study, but this is a good way to start. And I just want to say that this R bonus one is due on Lawn Kappa. I recommend everybody try it. It's really fun. It's looking at the experiment that we're analyzing, last semester's data. So, and I'm going to put your semester's data up as soon as the semester is over, or maybe during it we can start looking at our own data. So I think it'll be a lot of fun and interesting to see what you think. All right, so let's move on now to the document camera and get going. So we're right here on page 75, and we're going to be looking here at the two-sample z-test. Now, if some of you can't see very clearly, because for some reason some people might be having difficulty, it's not bright enough, just move up front. I see a lot of you in the back row, but if you have difficulty seeing or, back there, just come on up. There's lots of empty seats up in the front row. Okay, so now what we're going to do today is we're going to continue, and by the way, if you ever have trouble seeing or anything or hearing, whatever, just feel free to move to a seat where things are easier on you anytime during the lecture. Okay, so what we've been doing so far are these significance tests. And we, in the last one, we looked at, in 12 and 13, we looked at one sample test, so one sample z-test or one sample t-test. But often we're trying to compare two samples, like a treatment group to a control group, males to females, to see if there's any difference between the two of them. Like in your bonus survey, you're going to be looking at the difference between the online, people who are taking it online, people in person. So you often, the more common thing is that you're comparing two samples. So today we're going to look at the two-sample z-test and the two-sample t-test. And they're very similar to this statistic. Instead of having one sample, you have two samples. And the null is usually that the two samples average or percent composition is the same, that there's no difference between them. That's usually what the expected difference is. The null is that they're the same. Males and females score the same on the exams, or the treatment worked no better than the placebo. The drug worked no better than. It's usually the expected difference, that this is usually 0. And it doesn't have to be, but in the examples we're going to look at, it is. And then the observed difference is you see some difference in your samples, and you wonder whether it reflects a real difference in a wider population or not. So everything's the same here, except you have to calculate this standard error of the difference. You have to, it's not just the variation coming from one sample, you have to combine the variation coming from two different populations. So two different samples, both of your samples are going to vary. So how do you combine the standard errors of the two samples? That's what we're going to look at. So the idea, how do you compute the standard error for the difference? So just in general, think about it. You have two populations. So I'm just drawing these null boxes. Let's say it's population A, and here it's population B. And the null hypothesis, as we said, is that the difference between them is 0, the expected difference under the null. So that's the same thing as saying the mean of population A and the mean of population B is the same. We don't know it. That's why we're taking a sample, because we can't, sample the entire population. So we take a random sample instead. And then in our random sample, we observe some difference. All right, but the null is that they're the same. So now, what is the idea here? So let's just do a simple example. Suppose you drew a certain amount of tickets from each one of these, certain amount of people from each population, or what, and you get a sample average for both of them. And I'm just making this up. Let's say this was 100 and this is 90. So you see this difference, and you want to know that's the observed difference right here. But you want to change it to a z-score, right? So you have to divide it by the standard error for the difference. So that, of course, depends on the standard deviation inside this box and how many you sample. From those, you'll get a standard error for each one. So you'll get a standard error for the sample average. It's going to vary each time from A. That's what's changing. The population's fixed here, and every time we take a sample, we'll be changing our average. So what's the typical variation? That's described by the standard error for both of them. We're going to get for both of them. All right, and let's say this one was 4 and this one is 3. So now, I'm just making this up to show, how do we combine these two? How are we going to do that? Well, let's think about it. So this difference of 10 is going to bounce around, right? Each time we take a new sample. So our difference right here between the two samples is going to be what? Think about this. It will be 100 plus or minus 4 from this one. And then we're taking a difference, so it's minus 90 plus or minus 3. So you can see that the difference is going to be that difference of 10. But now the question is, how do you combine these two sources right here? What do you do here? That's the standard error for the difference. The standard error of, the absolute value of XA minus XB. X bar A minus XB, that's the difference. So how do you think I'll combine those? Well, let's think about it. You might think, to put 7 in here, plus or minus 7. Because you could get, but think about when that would happen. That would happen when these two are opposite sides. When you have, your sample happens to be high from this one, plus 4, and low from that one, minus negative 3. That would give you 7, or the opposite, minus 4, right? And then minus plus 3. So it's like when one is high and the other's low. That would give you, or vice versa, that would give you plus or minus 7. But that's not going to happen all the time, right? They're independent. These are independent samples. What you draw from here, and this is very important, it depends on this, what you draw from here, if you draw a high one from here, this box isn't going to say, hey, I'm going to give you a low one, or I'll give you a high one too. What would happen then if they were the same sign? Then it would be 4 minus 3. It would only be 1, right? Or negative 4 minus negative 3 would be negative 1. So it would be plus or minus 1. So it's not going, those are the extremes, but they're completely independent. And the formula for how to combine these two is by the square root of the sum of their squares. It's the Pythagorean theorem. It looks like that. And you can think of it, it's a nice way to think of it, because you can think, okay, if you have a standard error in one direction, let's say standard error of A, then right at right angles to it would be the standard error for B. It wouldn't, if you go in one direction, it doesn't tell you it gets they're completely orthogonal to each other. They're independent. So knowing one direction doesn't mean the other one's going to be more in this direction or more in the opposite direction. It's right in the middle. So you can think of it as, it's a nice visual here, as combining the two. Even though you're subtracting, it doesn't matter. It's plus or minus this difference. That this right here is the standard error for the difference. So it's figured like the hypotenuse. So a squared plus b squared equals c squared. And the proof for that is really simple. I wrote out a simple proof as I could, and I think it's in Appendix A. And you're probably going to be asked to prove this all the time in higher classes, so it's a nice intuitive proof you can look at. But here's the picture, even more intuitive. Okay? So what are we going to do? So the standard error for this difference would be the square root of 4 squared plus 3 squared. So that's what you would put in here. And notice that it's bigger than either one of the individual standard errors. We have 2 sources of variation here. So it's going to be bigger than 4, but smaller than the sum of the 2 of them. All right. So, of course, this formula does not apply if the 2 samples are dependent. And you can understand why. Because if they were dependent, it would be bigger than that. If they were negatively correlated, when one went up, the other one would go down, and you have a bigger spread. And it would be smaller than that if they were positively correlated. Okay, so it depends on them being independent. So let's now apply that to an example that I wrote a while ago, back when it was really it was very relevant back a while ago. Maybe these diets are still popular, but this was when this extremely low carb, high protein diet was very popular, called the Atkins diet. And so this was back in 2003. The New England Journal of Medicine did a really nice study comparing a randomized trial, comparing the Atkins diet to the conventional low-calorie diet. And the subjects were 63 obese men and women who wanted to lose weight, and 33 people were randomly assigned to the Atkins diet, and 30 were randomly assigned to the conventional low-cal diet. So in order to be consistent with our box models here that I just presented, why don't we assume that people were chosen from a population of thousands of people wanting to lose weight? Okay, so that would be the 2 null boxes. There'll be one for, just to picture it. And this isn't unrealistic. There are many, many people wanting to lose weight, and these were reflective. These people reflected a larger population. Okay, so this is the Atkins null box, and this is the low-cal null box. And in both of these, remember that the box always represents the entire population that we're drawing the sample from. So in both of these, we have thousands of tickets, and on each is written what? Let's read the problem. Okay, so assume the people were chosen, so the population, the whole population, that's the null boxes. Okay, after 3 months, the Atkins group lost an average here. This is the key word, lost an average, right here, of 6.8% of their body weight. This is not a percent problem. This is average. It's just they're recording it as a percent. Instead of in pounds, they're saying what percent of their body weight they lost. So there's 2 averages we're comparing. And here's the standard deviations of each of them. All right. So the null is that the average in the population and the average for Atkins and the average for the locale are the same. We don't know what they are, but our null hypothesis is always, is that this diet worked no better than this one. And what's the alternative in this case? Let's read the problem. Could this difference in weight loss be due to chance, or did the Atkins diet really work better than the locale? Okay, so if we're asking the question, we think there was evidence they thought that it worked better than the locale. So then the alternative is not that it's not that they're not equal, but they have a theory. They hypothesize, or we hypothesize, that this one worked actually better. So there'll be more weight loss. That's an L here for low calorie, sorry. That's an L. Any questions so far about why this is a one-sided greater than? It's just because the hypothesis here is that it worked better. If it was that we don't know, we think they're different, we don't know which one's better, then we'd put an equal sign there. All right, so now what did we do here? We drew n equals 33 from here, and n equals 30 from here, and it's without replacement. Why is it without replacement? Because these are separate people, so we're not gonna sample the same person twice, right? We pulled out, from all these people, they selected 33 separate people. So it's without replacement, obviously. And just about all samples are without replacement. The only time you usually see with replacement is for gambling games or games of chance, where the odds stay the same inside the box. Okay, so now what did we find out? So we got two averages from here. That's the X bar for here was 6.8, and from here, so that's X bar for the Atkins, and X bar for the locale was much smaller, 2.7. It's really hard to read up there. I'll put it down here. So X bar for the locale is 2.7. So that's what we're looking at. That's our observed difference of 4.1% of their body weight. Now the question is it big enough to be significant? So we have to figure out the standard errors. So the standard error of the sampling average from the Atkins, remember what it is. It's an average, so it's SD. That's an SD over the square root of n, right? SD over the square root of n. So SD, where do we get it from? We don't know the sigma here, and we don't know sigma here. So we're going to be estimating it from our sample, right? This sigma, we're going to be estimating it like this. That will be our estimate for this one, and for this one, it's 3.7. That's the estimate. Now, should I be using the t-test? I could use the t-test here, because why? The sigma's unknown here. But the sample size is large enough for our purposes. We've decided to cut off in this class of 25, and they're large enough that we'll just go ahead and use the regular SG. It won't make much of a difference. So the regular is 5 for this one. I should probably put that here too, so you can see it. So the SD for the Atkins group was 5. And the SD for this group is 3.7, just so you can see where I'm getting these numbers. Okay? All right, so it's 5 over the square root of 33 here. And this one's going to be what? The standard error for this sample, for the locale, will be what? Its SD, 3.7, over its square root of n. So those are these are the two ones we're going to be combining right here to get the standard error for the difference. Any questions so far? All right, so let's do that. So remember, our z is just going to be the observed difference minus the expected difference over the standard. I'll just write it one. This observed difference minus what we expect under the null over our standard error for the difference. Okay, so we've observed this difference of 6.8 minus 2.7. That's that difference. Minus our expected from the null is expected of 0. Now we just have to combine these two. We know it's 4.1 in the numerator, but what is it down here? So what we want to do is we want to take the square root of the sum of their squares. So we can write the square root sign. And if we square this, we get 5 squared over the square root of 33 squared, which is just 33. And if we square this one, we get 3.7 squared over the square root of 30 squared, which is just 30. So this is what when you do that, you get, I got that. And now we see a z-score of 3.72. And at this point in this course, you must realize that's going to be way out on the tail. Remember, 99.7% is between positive and negative 3. And this is even more than that. So we can draw the curve here, so you'll know that it's going to be way, way out on the tail. It's like that, and now that's as a z, and what are we matching it up with? We're matching it up as this difference, this in a percent difference, weight loss difference, weight loss difference, and we'd expect 0 weight loss difference, and we got what? 4.1. So that's what we're matching it up with. That 4.1 turns out to be a z equal to 3.72. And between 3.72 and z equals negative 3.72 is 90. We can look on the, since I'll just give you, you're going to have this chart. Why they gave me so many extra pages, I have no idea, that you have to carry around. It's very weird. But anyways, so we're looking at 3.72, and this will be the chart that you'll see on your exam, so you should get used to it. And here, it's between 99.978 and 99.982. So, I would accept you could round to the nearest line, or you could just, we might as well say 99.98. Okay? Anything in that range would be okay on the exam. I'll give you directions. So this is approximately 99.98% in the middle. So that means that there's just, on the two tails together, there's just 0.02%. So each one, which one are we interested in? Now this depends on our alternative. Since our alternative was directional, it tells us which tail. We just want to look at, we said that this is we thought it was going to be greater, that the Atkins would work better. So this is the percent we want, just that tiny bit. If we had had a non-directional alternative, we just thought they were different, that's a two-sided, two-tailed, and we'd have to include both tails. But this is for just because we specified a direction, we're just looking at this right here. And that, of course, is the p-value here is 0.01%. And it's 0.01 here as well, because it has to add up to 100. So, any questions so far? Yeah.
Why do you do both tails?
Why would you do both tails? Both tails, we're going to talk about that on the next page. So you want to wait till then? Yeah, we're going to talk about that right on the next page. All right. So when you basically, when you specify a direction in your alternative, that's specifying one tail. If your alternative is you think they're different, you don't know which one works better, but you don't think they'll give the same results. Yes?
So it's like a percentage. Are you supposed to multiply everything by 100 or no?
For this, the question here is, do I multiply everything by 100 because it's a percent? No, it's really not a percent. It's an average. Because these numbers are not 0 ones here. On each ticket is written how much of your body weight you've lost. So there's a number, percent of your body weight. It's a better way to do it because, 10% of your body weight, if you weigh only 100 pounds, is 10 pounds, whereas if you weigh 200 pounds, it's 20 pounds. So these are all different numbers. Percents, just like a label here, like your percent on an exam. Like if you put all the numbers in here, percents on an exam, they wouldn't be percents, they'd really be numbers. Not classifications as zeros and ones. Do you see the difference? Was that your question? Good question. Yes, don't get fooled by that percent sign. We don't mean, when would we use that? If it was what percent of the population in each group, what percent lost weight? Like 80% lost weight here and maybe only 70% lost weight here. Then it would be the answer to a yes or no question. All right, so any other questions before we move on? Oh, we've got to come to a conclusion. So what is our conclusion here? Let's think about what this means. It means that this is assuming the null to be true. This is assuming this null, that they're the same here. This is assuming the null. And if the null was true, we'd only see this big a difference. We expect 0 if the null's true. This big a difference, or more, or even more extreme, 1 out of 10,000 times. That's what that's saying. So 1 out of 10,000 times, if it was really just by the luck of the draw, like we drew another, 33 and 30 people in another, we did that 10,000 times, we'd have to do it before we'd see that big a difference. So it's extraordinary evidence. So you can say that this p-value is certainly less than 1%, right? And that's the null cutoff for highly significant. Remember, 5% was for significance, and this is the null cutoff. The conventional null cutoff for terming something highly significant. So these are very significant results. So we would reject the null, that they're the same, because look, it's only going to happen 1 out of 10,000 times. That's well beyond a reasonable doubt. That doubt that's left in our minds is minuscule. So we reject the null and conclude what? That there's extremely strong evidence that the Atkins works better to lose weight. The Atkins works better than low cal for losing weight. Now, if any of you are interested in losing weight, don't rush out and do this diet, because there's other things you might want to consider. For one thing, it's ecologically horrible. It's just eating meat all the time. And it's the other thing is that these people did lose a huge amount of weight, lost much more in the short term after 3 months. But the study continued and went 6 months and a year, and after a year there wasn't that much difference. with these between the two diets. It's a very hard diet to stay on, so people gain weight back. I just don't want to advocate it, even though there's overwhelming evidence for it. Look, it would be great if you want to lose weight for some particular occasion and want to do it very quickly. That's a good way to go. If you don't, but in the long term, it's not a great thing. Okay, just let's move on. And now, this semester, look at that, it's bleeding through. The paper's thin. Sorry about that. All right, so the question about one-tailed versus two-tailed tests. This will come up a lot. So you'll also see it's the same thing as one-sided versus two-sided. So specifying a direction to the alternative is called a one-tailed test or one-sided, same thing. You'll see it either way, one-sided. And if you don't specify a direction, just specifying an inequality, that's called a two-tailed test or a two-sided test. They're used interchangeably. Okay, now, one-sided and two-sided tests yield the same z for both, z or t. But the p-value of the two-tailed test is both tails, is double the p-value of the one-tailed test because it's the area of both tails. The p-value for the two-tailed test. And the p-value for the one-tailed test is just equal to the area of one tail. Okay, so you can see the relationship there. Now you want to know which test should be used, all right? Well, that depends on which alternative makes sense before looking at the results. So, like if you have evidence before looking at the results that you think this Atkins diet is really something new, really good, or you have evidence that it works before looking at the results of your data, then go ahead and use the hypothesis for the one-sided because it's going to yield a smaller p-value, which will give you greater significance. And everybody wants more significance so they can get published, because they can show that something worked. But remember that you have to formulate your hypothesis before looking at your results. A hypothesis is you're doing this, you form a hypothesis, and then you collect data, right, to test the hypothesis. So you can't then change your hypothesis once you look at the data. That's cheating. Okay? After you look at the data, you know which way. So the difference went. So it's cheating to use that knowledge to formulate your hypothesis. Changing your hypothesis after looking at the data is very serious, and a lot of people, it's called, you probably have heard this term, people refer to it as either data snooping or p-hacking. It's one way to, it means that you're basically cheating. It's called data snooping. That's a very common word, or more commonly now, there's other ways to p-hack, but to hack your p-value, to make it go in the direction, to make it smaller because to get more significance. So even if you didn't know which one worked, after looking at the data, you say, now I know, and I need a p-value less than 5%, so I'm just going to pretend I had a one-sided test to begin with. And how would anybody guard against that? It's really hard for people, they can say, well, that's what I thought to begin with. So to guard against people doing that, many journals, for sure, and software programs always use or require two-sided test. But it really doesn't make sense it makes more sense to use the p-value that fits the correct alternative hypothesis. The only reason people always use the two-sided is to guard against people doing this stuff. All right, so the picture is this. If you have a one-tailed alternative, like you could say, it could be, then it's just the area of one tail. So you could say, for example, in our example that we just used, I'm going to make it look like we got a little bit less of a z, so you can see some area there. This would be the Atkins is better. And that's what we did. And then the other one-sided could be on the other side. And this is the Atkins, if you thought the Atkins was worse. Okay, the Atkins is worse. I guess you have to, before you look at your data. Okay, so these are both, just for both of these, it can go in either direction. You want the P is equal to the area of one tail, or one side. And that's what we did when we got the 1.01%. But let's say we didn't know. Let's say all we thought, we didn't know which was better. We know that they're probably going to be different because they have different mechanisms, but we weren't sure which is better. We're comparing two diets, and we really weren't sure to begin with. Then, since you don't know ahead of time, when you get a particular, you get that same Z, whatever it was, we get the same Z, but we're saying it could have just as easily gone the other way, because we formulated this ahead of time. So then you have to count both tails. Because, you didn't know which direction it was going to go with. So you have to, it will give you twice the p-value. So on our previous page, if we had done that, a two-tailed test, let's just look back, what would we have gotten? If this, first of all, if we had done not equal here, then we would have had to include the area of both tails, and we would have had 0.02%. We would have had both sides. Yes?
For this one, didn't we look at the data and then say that?
We did for the example. We weren't supposed to. We did just because we saw the data ahead of time. But if you were the researcher, you would have to formulate this ahead of time. Her question was, didn't we look at this first and then didn't we just p-hack? Didn't we just data snoop? Well, for the example, we did the results, but if we were doing the experiment, we'd have to state these before looking at the results. Does that make sense? Does everybody understand? If you're the researcher, you have to state this before the results. And I think they did do this. They did think that the Atkins was going to work better because they had a lot of evidence that people are losing a lot of weight from it. But either way, this is so overwhelming evidence it hardly matters in this case. It makes a big deal when you're sort of like near 5%, or between 2.5 and 5 for the one-sided, because then if you did the two-sided, you wouldn't have significance, and people care about that cutoff. All right, so now let's move on and to the next page. We're on 78 now, and so this is, okay, so what we did here, let's just remind ourselves, when you're looking back at your notes, here we did the two sample averages. So this is comparing averages here, right? So this is the two sample Z for averages. And now we're going to do the two sample Z for percents. And it's basically the same thing. We just have 0, 1 boxes. Okay, so now, so Gallup asked a random sample of 500 men and 500 women if they'd ever fallen in love at first sight. They do this often on Valentine's Day. They ask a lot of love questions. And 44% of the men and 36% of the women said yes. Is the difference in response likely to be due to chance variation or not? Perform a significance test. Now, which of the following is the null hypothesis? The null hypothesis is going to be the same whether you looked at the data or not. What's the null hypothesis always? That the two are equal. But what's equal? Not that these sample percents are equal. They're not. But that the population that they were drawn from and the mu's are equal. Actually, these are percents, so we need new notation. So let's use notation. If you have a 0, 1 box, the mu's are percents, so we'll call it, it's the Greek letter is rho, but it looks so, looks so much like a P that we're just going to use a P for population, because you won't be able to tell the difference. Population percent. And then we'll use a P hat for the sample percent. And this is done a lot, putting a hat on something. So, all right, so we'll use that because otherwise the Greek letter would look so much, it would be hard to distinguish it. So so which of the following, which do you think? So the difference in population percents is 0, right? Not sample percents, never say that. It's the population percent. The null, and the null box is always about the population, not the sample. Okay, it's always about the population. You know the sample. The sample is going to give you some evidence, like how likely it is from certain population. You're trying to estimate population percents that you don't know about. So another way of writing this is that H naught is what? The difference is 0 is the same way as saying in the population, the males who said yes is equal to the females who said yes. The population percents are the same. All right. Now, let's do some eye clickers here, and this is the first one. Suppose before looking at the results, you thought, we're just going to do these 3 here in your notebook. So let's look at them. Okay, so now let's stop it and great. Just about everybody got that. This is one of our best. Great. Okay, so let's look at the next one. So it should be two-sided because you looked beforehand and you didn't know who was going to have more yeses. So let's look at the next one, and we'll start this. Move it out of the way. Okay, ready to stop? Okay, let's stop it. And let's see. Good. Keep two-sided. Why? You can't. Here, let's look at this. See, See, this would be cheating. This would be data snooping. You want to keep it two-sided because why? After looking at the results, you can't then go back and make your hypothesis coincide with the data more closely. You thought beforehand that you can't just go back and change your hypothesis. Your data you're taking data to test your hypothesis. So you can't cheat and go back. All right? Now let's look at the next one. So it's keep two-sided. Let's do the next one. All right, let's see what you say here. We'll stop it. Great. Yes, most people got this. One-sided, you can change it if you go ahead. You learn from your first experiment. You learn something. You learned after you collect the data. Now you see this. You didn't know ahead of time. Now you see that men are more likely to say yes, and you believe it. So you can use that new information and test that new information. So you can then you could go ahead and make a one-sided, and as long as you collect new data. So let's write that down here. So for B, we said before looking at the data, okay, you didn't know which direction, so you just said the alternative is that they're not equal. But after looking at the results, you can't go back and change that. That's data snooping. You have to keep it two-sided. But if you want to collect more evidence and do another independent survey, that results aren't connected to the last one, a new independent survey, now that you have more information, you update your hypothesis, and now you think that it is one directional. You could think that now your alternative hypothesis is that the percentage of males in the population is going to be greater than females. You're updating your hypothesis, then you take a new survey and you collect new data. That's fine. So why don't we go ahead and do it for both ways? And remember what we're doing. We have this, our null is that there's no difference in this population between the percent of males who would say yes and the percent of females who would say yes. So we have these two boxes to visualize what's going on. And there's millions of tickets in each of them. And it's a yes, no question. So here's the males, and it's the whole population. It was a nationwide survey. Here's the females. And it was a yes, no, and we're coding it as ones. If they answered ones, that's yes. And if they answered no, we'll put zeros, because we're looking at the percent yes. And it's the same here, Okay, so it's the same thing, so let's do this. So we have ones and zeros. And here we have ones and zeros. But we don't know this percent. This is unknown. So we'll put a little question mark, unknown percent. Of course, it has to sum to 1, but they're unknown. And then our alternative, what does it say? Let's do both of them. We can do both of it. So the alternative we'll start with this one. Because I would think that most people would think that men just respond to looks more, I think. You know, I think love at first sight is just how somebody looks. And I would think that men are just more, women would respond. It's not that women are even any deeper. They might think more about things like how much money they have or something. But I'm not saying that. I'm just saying that men just seem to respond more primitively, maybe, or directly. Okay, so now, so we've got this, and now what are we doing? So our N is the same, 500, and all surveys are without replacement, but that's not entering in to any of our, this doesn't enter in the population size. It's only the sample size, because this is a small fraction of the millions. And now we just have to do these standard errors. This is good practice. Okay, so we're doing the standard error for the sample percent of the males, and here's the standard error for the sample percent for the females. So what does that mean? Remember, it's the same thing. It's SD over the square root of n times 100. All right, but what's the SD in this case? Well, that's going to be estimated from our sample. And for the men, what did we get? We didn't even say what we got here. We forgot to put, here, I'll put it here, that we got a p hat of 44% here. So that's what, in here, we got a p hat of what? Where am I getting it from? Up here. 36%. So this right here gives us the standard deviation, right? We're going to estimate this to be 44%. We're going to estimate that, and then that will give us an estimated, so we'll estimate to be 44%, and we're going to estimate this to be 36%. Okay? And that will give us an SD, an estimated SD that's very good because it's a 1-0 box. And that's 1-0 boxes their SDs don't change that much. Their SDs are tied to their means. That's why they don't change very much here. They're tied to it. This will give you the other, unlike with the mu's, the averages. So we get the square root of p as a decimal times 1 minus p over the square root of n times 100. And here, we're going to do the same thing, but we'll get the square root of 0.36 times 0.64 over the square root of 500 times 100. Okay, so we have those two. And this one is 2.22%. That's one standard error. And this one was almost the same. It was just slightly less, just because this standard deviation is slightly less. And that was 2.15%. So that's all we're doing here. And now what are we going to do? We're just going to do z. So by now we know it's the difference between these two. 44% minus what? 36%. So that's an 8% difference, but we don't know how big or small it is until we compare it to these. So we're going to combine them, and we're going to expect to get something bigger than this one, bigger than the bigger one, but smaller than the sum of them together. So we got the square root of 2.22 squared plus 2 squared. Oh, this percent sign makes it hard to see it, but 2.15 squared. And what is that? It's 8 divided by 3.09%. So what I'm saying is this 3.09 is bigger than this, either one of these, bigger than the biggest one here, but smaller than the two added together. So make sure that's the case. And I divided them, and I got 2.59. So that's a big z-score. That's a very big z-score. And if we wanted to figure out p-values, we're just going to have to just do the normal curve. And, on your homework, you can use the p-value calculator. We'll look at it for the t-test, which is coming up in a minute. But this is about 99% between Negative 2.59 is a z, and 2.59 is a z. So if we were going to do a okay, so now for this, for this alternative, we ended up getting, so we have two alternatives we're trying out here. Or if we started off with this one. Okay, so this one, the two-sided one, the P for the two-sided, two-tailed, this one, is going to be the area of both tails. So that's 100 minus 99. And obviously the P for one tail test, which is the directional one, the one tail is specifying which way it's going to go. This way. It's going to go this way. It would be this one for the one tail. Is equal to 100 minus 99 over 2, which is just half of it. So that's pretty clear why people do the one tail, because they want a smaller p-value. They want more significance. In this case, it doesn't matter, but let's say it was for the two tail was like 6%. That wouldn't be significant, whereas for the one tail, it would be 3, so it would. So that's why people, that's why journals just about always want you to do the two-tailed. Do you have a question back there, either one of you? Yeah?
Yeah, I just, like, is it 44 minus 36 in that order because our hypothesis is that the male was bigger?
Yes, yes. It's in this direction because our hypothesis is that the male was bigger. If it was the other way, it would go in the other direction.
Okay, thank you.
All right.
For the p-value, you just have to say it's like 0.01 or like 0.005, right?
For this one, you'd say 0.5%. If you said you'd say 0.005, you'd have to move 0.5%.
Can I move the decimal over? That makes more sense to me.
As a decimal,
Yeah.
then you'd say this is 0.99. Instead, if you want to do it as a decimal, you'd say this is 0.99. You'd say 1 minus 0.99 over 2.
Just because you know how it's like if you p is greater than 0.05, you see like.
Yeah, just get used to going back and forth. For some reason, her question is, should you express it as a decimal or as a percent, and she wanted to be consistent. For some reason, statistics lingo is not consistent. They always call the significance level, the null cutoff, alpha equals, and they express that as a decimal, alpha equals 0.05. But then when they're doing the p-values, they usually do it as 5%. So you just have to get used to going back and forth. Was that your question?
So if I do the percent, can I say, oh, I'm rejecting the null because it's less than 5%?
Yes.
So it's either just say with percents in my explanation or say with percents.
You can say, yeah, they go back and forth. You just have to get it, because they say alpha equals. For some reason, when they do the significance level, they call it as a decimal. Just get used to it. I mean, it'll be pretty clear. Usually they say 5%, though. When they say the p-values, they say the percents. Okay, so now let's see. So that was, read the summary, of course. And now we're on the t-test here. Now this is the same exact thing, except we're going to use the t-curves. And we're going to use standard error plus. So notice it's the same exact thing. Here's for the z and here's for the t. All right, so now when are we going to use the t? Again, it's when we have the unknown sigma and a small sample and the population's close to normal. All right? If it's not normal, then you're going to have to do something. Small samples that aren't normal, you're not going to be able to use either z or t. But if they're normal and the sigma is known, we use z here and we use t here. Okay? So this qualifies right here because we have those. All right. If our sample's small, and I told you for the purposes of this class, less than or equal to 25, but sorry, just wrote less than 25. I'll specify on the exam if I gave you one that was 25 exactly. Okay, and from roughly normal populations, an unknown sigma. Okay, so those three conditions. Then the only difference is in how we compute the standard errors. And another way we could do this is this is the same thing. Well, we'll just do the example. Why don't we do that? Now, this degrees of freedom here, how do you combine their degrees of freedom? The two-sample t-test doesn't exactly, the two-sample t-statistic, the statistic with one sample follows a t-curve. But with two samples, it doesn't follow the t-curve. So deciding how many degrees of freedom, if you have two different standard deviations here, so is really problematic. So we're just going to use this simple conservative approach. Now, I just want to warn you, if you're going to do the R bonus, they're going to use something more complicated called a Welch's t-test. It's if you just give the command in R for the t-test, it doesn't do this two-sample t-test with these degrees of freedom. It does the same thing, but it computes the degrees of freedom differently. All right. Now, so let's look at this example. We have a randomized double-blind test, which was done to test the effectiveness of a drug. All right. Designed to improve memory in Alzheimer's patients. So 20 people took the drug, and they were randomly assigned, and only 16 took the placebo. And this is they were given a pre and post memory test, and how many words did they recall? So in the drug group, they recalled 3 words versus 1 here. And here's the standard deviations. So now, let's see. So you just had the post-test minus the pre-test. So some people did worse. That's why the standard deviations are high. Some people got negative scores. So the null hypothesis is always that they're the same, that the drug is no different than the placebo, so that their difference is equal to 0. So the mu for the drug is equal to the mu for the placebo. Now, suppose you had prior evidence that the drug works. Then you could say the difference is greater than 0 and do a one-sided test, that the mu for the drug will be greater than the mu for the placebo. But suppose you have no idea if the drug works at the start of the study, but after looking at the results, you believe it does. Then you have to stick with this two-sided. You can't cheat and say, oh, I saw a difference, like looking at these results. You have to come up with your alternative ahead of time. So let's just do since it's just the same as the z, let's just go ahead and do it. The t is equal to, you're going to have your observed difference, which in this case is what? 2, 3 minus 1, minus your expected difference under the null, which is 0. Now the difference is going to be, you're going to do a standard error plus for the difference. It's going to be a little bit bigger. All right? So the difference we know is 3 minus 1. So we want to see if that's how much better the drug group did. And now how are we going to compute this difference here? Well, let's just think about it. The standard error plus for the drug is what we're trying to get first. And remember, that's SD plus over the square root of n. So we could have multiplied to get SD plus. I'm not going to do it this way, but to get SD plus, you could have multiplied this 4 by the square root of, you want to make it a little bit bigger, so you do it by square root of n over n minus 1, because that's a little bit bigger than 1. Because the way this was already computed, but you would have originally divided by n minus 1. So to change it, you make it a little bit bigger, and you would have done this, so that would be 4 over the square root of n here is 20 over 19 for this one. So now, and for 3, you would have done the square root of 3, and you take n for 3 as 16 over 15. But it's an easier way to do it in this example, and that is what? To just know that this is the same thing as taking the regular, instead of doing it up here, you multiply that by that factor. It's the same thing. You could just do this and divide by n minus 1. So you could take your given SD and divide by square root of n minus 1. Those two things are the same. You can work out the algebra. It's the same. We did it last time. So then if we just do it this way, we have 4 over the square root of what? 20 minus 1 is 19. And then for the standard error plus for the placebo, we can do the same thing. And there we'll just have what? 3 divided by its sample size minus 1, which is 15. So those are the two right there that we can put into the square root of, right there. So we'll have 4, we're going to square that. So we'll have 4 squared divided by 19, because square root of 19 squared, plus 3 squared divided by the square root of 15 squared. So it's just easier to do it like that. So this is equal to 2 divided by 1.2 is what I got, which is equal to 1.67. So that is our t. Now, and then you have a problem like this on your homework. It's due, is it Thursday? I think it's due Thursday. So now, what do we want to do? Find the p-value. Okay. Well, we got to do the degrees of freedom. How many degrees of freedom? Well, remember what we're going to do. The degrees of freedom are equal to n minus 1 for the smaller n, for smaller sample size. So it's going to be equal to 16 minus 1, which is 15 degrees of freedom. Okay? So now we have to look at, so we'll draw this t-curve somewhere. And now this is the t-curve for degrees. Now if we look at the back of the book, it's going to give us a big range. If we want to get a more exact, we'd have to look on our p-value calculator, and we're going to look up 1.67. So why don't we do that? So, or do you want me to just tell you what you got to save time? Tell me what, do you want me to tell you, or do you want me to, raise your hand if you want me to go to the p-value calculator. Do you want to just see it after? I can show you after class for those who want to see it. Okay, how about I do that? All right, so what I got on the p was 88.4%. Okay, for what? Between 1 t is equal to 1.67 and t is equal to negative 1.7. Right? Now, if I did want to look on what you're going to have on your exam is, I'll show you what is just this. So I'd look for 15 degrees of freedom here, and it would be right in between. I'd just look at this line right here, and 1.67 is right in between those two. Right? So it so for the one-tailed, it would be the one tail that just does would be between 5% and 10%, but I don't know what. Okay? It's closer to this one, so it'd be closer to 5%, but still it would be hard to tell. Okay? So now I got 88.4 in the middle, so that means on the two tails together, what do I have? I have 11.6, right? So the two sides together, 11.6. So each one would be 5.8%, and this would be 5.8%. So we can say the one-sided p-value The one-sided p-value is equal to, we'll just do the two-sided p-value, is equal to 100 minus 88.4%, and that's 11.6%, right? And so the one-sided p-value is equal to 11.6 divided by 2, which is 5.8%. Now the last one we'll do is an eye clicker, and then we'll go. All right? Does everybody understand this? Any questions on this? The two-sided would be both tails, and the one-sided would just be one of them. Yes?
How would we calculate on the test if you said we would use that chart, but you
I'll just give you multiple choice, like between 5 and just exactly. Like it would all, it's all multiple choice anyway. So it would be the only answer between that would be possible. Her question was, if it was on a test, how could they use a chart? And I said it's going to be multiple choice, so there'll only be one answer that would fit. All right, now let's just do our last eye clicker question, and that will be it. So we'll start this. Now, this is the bottom of page 80. If you use the z-test, think about it. Would your p-value be bigger or smaller than with the t-test? And remember, p-values measure the area in the tails, and t-curves have fatter, bigger tails. So which is going to have the bigger p-value, t or z? So this question asks, if you use the z, would the z p-values be bigger or smaller? Okay, and let's stop it. Sorry. Whoops. What happened here? Okay, let's stop it and see. And what you said? Yes, they're always smaller using. So let's look over here and just fill that in the notebook. So p-values using z are always smaller than using t because the tails are smaller than the z, because t has fatter tails. So it's bigger p-values. T has fatter tails. All right, that's it. And so see you next time.